Okay, well, this stems from a science fiction, a set of novels by Li Shu-shen called, well, actually his trilogy is The Remembrance of Earth's Past, but it's gotten to be known as the three-body problem. And if any of you happen to have seen the streamer, I think it was on Netflix, that's season 1, there's an interesting propulsion system system in there. It stems from this. Originates way back in the late 50s with Project Orion. And as you all might know, this was actually really well funded for a while idea of using nuclear bombs to propel a ship. It ended in 1965 when the funding was just closed off. Interestingly enough, in the early 90s, a guy by the name of John Dale Solom redid Orion in a system called Medusa, and that was, he sort of replaced the ship with what I would call a sail, and but you still carried the nuclear pulse units aboard. So both Orion and Medusa were subject to the tyranny of the rocket equation. When I saw at the bottom of that slide is a frame from the three-body problem, and this is a system. Shin invented it, and as far as I know, I have yet to find out where the heck the idea came from, except from Lu Shen. And the idea is you construct a nuclear bomb runway. The concept of runways with like pellets for scooping to use in a ramjet, for instance, go back, and there are several others. But I've never seen anybody propose constructing a runway of nuclear bombs. And Shin had, on the show they have an explicit construction of the whole thing, and I noticed that it's similar to Solom, except that you put a payload on a system that's got a sail, and you phase the runway so that you propulse the whole system forward up to 1/10 the speed of light. It turns out what I tried to do was construct a toy model of this, and the whole idea was to try to achieve 1/10 the speed of light with a sail system. And the one thing I did was I picked a material which seemed like it's ideal, and it's graphene because of its thermal properties and its material strength. which are absolutely remarkable. And so it looks like this. Now, I replaced the payload. I put the payload on the sail itself. You may notice that sail looks a little bit like it derived from Starshot, and it is. But this is a candidate model, and just to see if you could make the thing work. The interesting thing is that the sail, I made it 5 microns thick. So if you calculate the mass, and I made a 25, well, I made the whole mass of the thing similar to Shen's staircase ship, except that I embedded the payload instead of having it back on lanyards and the trailing. And by the way, in the novel, somebody's brain is in the payload. But this one, I'm just making an instrumented payload for delivery. And in the novel, it's delivered to Alpha Centauri. Very strange to me, but how he picked that out. So that's the ship there. One of the things that's added in is the mass of the sail, which is calculated by its size, which I just picked at 100 meters for a candidate size. And so well, I just have to go back and say, the delta V is easy. I mean, per pulse, the delta V is pretty easy to calculate if you make the sail such that it intercepts a directed nuclear explosion. And I've got to say that there's, well, things that you have to consider, that when you set off an explosion, are you going to, 1, rip the sail apart, 2, are you going to melt it, and then there will be a third constraint, that the acceleration can't be greater than the possible constraints on what the instrumentation can take. And, oh, shoot. So you can see the paper. If you calculate the mechanical, in other words, the yield stress on graphene is tremendously high. And you look at what kind of standoff distances are safe for setting off an explosion, then you get these expressions. So as you can see, there's one for the mechanical strength, one for the thermal, and one for acceleration. And I wrote them in terms of the pulse length, the delta T. By the way, one of the complications here is that you have to you have to calculate the free expansion of an explosion in a vacuum. And I'll be darned if all of this wasn't done by Freeman Dyson in 1958 and for Orion. And by the way, those are for directed explosions, not exactly for spherical, although you can use that. I mean, that's what was used in the novel, although no technical details are really given in the novel. But anyway, As far as I can tell, those documents from the late 1950s are still classified. And so I just had to, do what I could. And it turns out really that the mechanical, the stress on a graphene sail is kind of drops out of the constraints. And so this is a plot of yield, of the standoff distance, the safe constraint distance. And what you see is that thermal dominates the constraints. The acceleration, by the way, I looked up what the constraints are on that, and the military spec documents have 20,000 Gs, and so I picked that. Apparently that's the limit that you can do artillery instrumentation. Apparently it could go up to 100,000, but I didn't use that. And I'm getting a little ahead of myself here. If you just go an instantaneous pulse against a 100-meter, 5-micron sail, graphene sail, then, of course, the bottom line here is how many bombs do you need to get the thing up to 1 or 2% the speed of light? Well, if you just do a delta function impulse onto the sail, then it turns out that you need like thousands of nuclear bombs. And by the way, Shin had like less than 1,000 in the novel for Staircase. So I'm borrowing from, I suppose I'm borrowing from Dyson. One of Dyson's memos, there are 3 of them on free expansion in a vacuum, says Gaussian free expansion. And the only other thing I could think of was that, and I know that Orion was using directed, and that means shaped charge impacts on the Orion vehicle, said Gaussian. And so I thought to myself, well, okay, what if you just shape the impulse? Not an easy thing, or not, in fact, I don't really know how you do it. But what you see is that the acceleration, you can see there in that one plot that the acceleration is kind of ramps up, and then you make the height of the Gaussians the constraint values for a given yield, and sure enough, and it's especially interesting for the thermal one, that you can keep it below 4,500 degrees Kelvin. By the way, I picked that number because that's probably not realistic for graphene, but it's a theoretical limit that's possible. So here's what I got running through the modeling for a 1 kiloton yield. You need 942 pulse units. For 2 kilotons, it's 666. I cannot believe that number came out at that. And a 10 kiloton pushes the peak acceleration pretty strongly. So I decide, and in the novel, he doesn't really say what the yields were, but I'm going to keep them at 1 and 2 kilotons. Interestingly enough, if you model the thermal properties, and graphene has great thermal properties, especially if you kind of treated the graphene for its thermodynamical properties. That this is a plot of the thermal response, and there's it's I think 7/10 of a millisecond for the well, I should say that I fixed the standoff distance to be 7 kilometers just to fix it, and the pulses look like this. There's a instantaneous is a delta. Well, I don't want to do that because that'll probably melt the sail. But there's a square distribution and a Gaussian distribution, and both of them fall way below 4,000 degrees Kelvin. So graphene works. Here's a toy schematic representation of what's going on. Is you have the pulse unit, and by the way, it's best to use fission because with thermonuclear you produce a lot of neutrons. With fission you produce a lot of X-rays, and it's a lot easier, best I can tell from all the literature, to create the directed plasma. And by the way, the whole idea is that plasma is, even though it's just a shape here, supposedly when it reaches the sail, it fills it exactly. Now, that's something that's probably not possible, but I propose that would be the thing to use. Then what's the runway like? Well, for a 2 kiloton assembly of pulse units, and by the way, I guess I should have mentioned that I've got a guidance, navigation, and control system, not only on the pulse unit, but also on the sail. So everything gets lined up, and all of the dispersions are taken care of during operation. Well, that's a representation of taking off from Earth orbit or near Earth orbit. And it's interesting when you go so fast. After about the second pulse, you're at solar system escape speed. I want to note that it's only like 39 lunar distances, the distance from the Earth to the moon, to get up to a tenth the speed of light with the 666 pulse. That's one thing where Shen missed. It's very interesting that when you look at the mass properties of his probe or his ship and the payload and mass distribution, it really actually works, except that he has the pulse units distributed between Earth and Jupiter. Well, you don't need it that long. You're going so fast by 39 lunar distances that you're completely rectilinear. and very, very quickly. So that's the one thing he got wrong. So in conclusion, it looks like that the physics actually works. You're able to construct a nuclear bomb runway, and how you do the pulse shaping, I don't know. I looked up, there's a possibility of using magnetic fields. Of course, everything happens so fast in a nuclear explosion that how you line up the technology for that, I don't even know if it really can be done. It is interesting that now a 5 micron thick graphene sail you couldn't make today. This is all future technology, if it's possible at all, because layered graphene has all kind of irregularities in it, and nobody can really do that these times. But it's possible in 50 years that you can. The one thing I left out was that once you're in cruise mode, you're going to be at 1/10 or 2/10 the speed of light, running into the gas and dust of first the solar system and then the interstellar medium. Well, it turns out that some calculations show it's about the same as with Starshot, although you do have a large payload here instead of 10,000 1-gram ships. But it looks like that with like Whipple shields made out of, you can make, I guess it's called Aerographene. It's like aerogel, and you can shield the payload with that. So my conclusion is that it's possible to do this. I don't know why. If anybody here has ever seen this before, as far as I can tell, Shin is the first person to ever think of it. I mean, I've actually worked on something like this a couple of years ago and trying to do it with one bomb, and it doesn't work. But when I saw this on the TV, I thought, has anybody ever thought of that before? And as far as I can tell, they can't. They haven't. I mean, putting 1,000 nuclear bombs in orbit in the solar system is, I think, still politically prohibited nowadays. But there are 22,000 nuclear weapons in the world, so it's not too bad a use of these things. So thank you.
I can see why you'd want the sail to have a standoff of 7 kilometers from a bunch of nuclear bombs going off. I get that. But from the geometry you showed of looking like a parachute, the cables are going to be a lot closer to that detonation. How do the cables survive?
I don't have cables. Mine.
Is there not a payload trailing along behind, or no?
No.
It's all in the sail?
It's
Okay.
a standalone sail. I mean, Solom has that, and he actually calculates all of the parameters you need to know. If you look at his 2 papers from the early 90s, he figures out the thermal properties that are needed to have that parachute-looking type of device.
All right, thanks.
Do you know if anybody's done any kind of spectroscopic analysis of those types of explosions before? If they tend to be just black body emitters, or if there's other type of characteristic peaks in there?
Well, let me kind of answer that in a different way. Apparently, it arose out of Orion. Orion was configured in such a way that the nuclear bombs that were used for propulsion were focused onto the plate. And I suppose Dyson was involved in this too, but a bunch of people were. Doing focused nuclear explosions is something that is really highly classified. There's a thing called the Casaba howitzer, you may know, and that was apparently it was actually tested by, well, it was Livermore who did the test. And you know, there was a system called, I can't remember the name of it, where they were trying to produce an X-ray laser for Star Wars, well, for the SDI. And that apparently didn't work. It's one reason I excluded radiation as the propulsive method and used just a plasma from, you know, X-ray. Well, you have it's a complicated system. You have you put like titanium into a cylinder, and then you set off a fission bomb, and it converts, of course, the tungsten into a plasma, and that's what impacts the sail.
Okay. I was interested because one of the possibilities to limit the thermal damage to the substrate, whether it be graphene or whatever it happens to be, is if you could follow that with a stimulated laser beam, you get a relaxation, a thermal relaxation, so that you could recover a bit of your safety margin, and at the same time, you're essentially emitting energy from the spacecraft, so you get an additional energetic boost, which I think would be kind of interesting to consider. So
Yeah.
let's talk about that more, for sure.